This is CPE 233 Lecture 25 when we have an example here. So this is a classic hardware modification problem, which is what we want to do is modify the RISC-V hardware to do something different. And so I like these problems because the only way you can do them is if you understand the RISC-V architecture and the instruction set. So let's take a look at this problem. And so essentially this is, you can read through this. What I want to do is add these two instructions here, which is BB set and BB clear. Essentially, roughly what this means are branch if bit set and branch if bit clear. Now these, there's not a lot of description of these instructions, but all the description you need is sitting here in the comment of the instruction itself. So these are example problems. They would actually kind of look like this: B set x10 x11. They would look like that. So it would actually call out registers. So the first thing to notice about this problem is it looks like a branch instruction, and it has the same format as a branch instruction. So that's good, so we can leverage that, most likely anyway. And the other thing here is we got to understand what this problem is going to do. So we're going to say branch if this bit here is set. Essentially this is an index value into this register. So it looks horrible. This is an index, and it's going to index into the bit locations into this source register here. And based on that, it's going to decide whether to jump or not. And same thing with a clear, but it's, it's opposite of BB set. So this problem, once again, we are adding stuff. We're adding instructions, so we're going to be aware that things are going to grow. Maybe the memory or something like that, so we're going to be aware of that. But let's might as well get into this problem. And I don't really know how to do this other than to talk about it. So this instruction here, and let's go back on that one real quick. So the other thing to notice here is that since this RS2 is an index, I'm only going to use the bottom 5 bits of it. Now this is very similar to the shift instructions as well. So let's look at the hardware here, and this is our final RISC-V Otter hardware. And what we need to do is, this is a branch drive instruction, so I'm going to look at this and say everything's based on RS1 and RS2, and so that's already input to these modules. And so what I'm going to need to do here is, I don't need to put any more inputs to this thing, but I'm hoping I can just reuse this module here with some modifications. So before we do that, let's look at this. Let's look at these instructions here. But particularly the branch instructions. I want to see if I can use the same opcode. I'm breaking out my notes here. That's what that crinkling is. And so I'm looking at the branch instructions, and there are 1, 2, 3, 4, 5, 6 branch instructions that go from 1, 7, 6, 5, 4. That's missing a 3 and 2. Okay, so essentially we can keep the same branch opcode, and that's going to be really important. What we need to do is add 2 more func3 codes. Now the func3 is a 3-bit field. With 3 bits I can get 8 unique numbers. 6 of them are already taken up, so this will be the extra 2. So we don't have to make any major modifications to anything. We can just completely reuse that branch instruction format. There's enough room for it to fit in with that 7-bit opcode. We just have to take those 2 last spaces for the func3 code and add those in there. So it's gonna fit in there really nicely. Okay, so the other issue for this we want to worry about is how am I going to do this? And essentially it's very similar. I think what I'm going to do here is very similar to the other branch instructions. There are 6 branch instructions. Those 6 branch instructions are based off of these signals right here. Now these, I don't know what if I could, I guess I can't scan in on this one. Okay, these 3 signals cover the 6 branch instructions. Okay, I know there's a lot more pseudo instructions, but we're not going to worry about those. So what we need to do is add the hardware in here to support these 2 instructions. And I believe we can do that by simply, let's do this, by simply adding another signal here, and we can just call it BB, I forgot what I called it. BB anything. BBSC, BB set clear. So this is a single signal, and the output of this signal can be essentially the bit we're looking at. And so all we need to do is put some hardware inside this branch condition generator to support sending that 1 bit of interest, the one that's called out by the instruction. What we're going to do is send it over to the decoder. And so this is very straightforward. I don't want to do the whole thing here, but this is going to be RS2. This is going to be BBSC for set clear. So here's your input signal. And here's this RS1. So RS1 is going to feed into a 32 to 1 mux. RS2 is going to decide which of those bits is sent over to the decoder, and the decoder is going to look at those and decide what to do based on the instruction. So this is very much like these instructions here, where there's only 3, but it controls 6 instructions. What we have here, we've added 1 signal. That 1 signal is going to control 2 instructions, and so that's going to work on that. I think that's all we need to do for that. We need to make the decoder aware of these 2 instructions here. No big deal. I think we're done with the decoder. As far as the state machine goes, we didn't add any extra states, so we don't have to do that. We didn't really modify the branch instruction in such a way that we need to modify the state machine at all. It's just another type of branch instruction. The branch instructions in the control unit state machine, very generic, unlike the decoder where you have the big case statement in there. So no changes to the state machine. All of our changes are to the branch condition generator, and put some changes into the decoder. Okay, so I think that's part A. It supports it pretty nicely, just adding a couple of pieces of hardware. As for the assembler, we're going to have to tell the assembler, hey, we got 2 new instructions, and these are the Func 7 and Func 3 opcodes, etc., etc. When you see those instructions, send out the right instruction word. Okay, so what else do we got here? Changes in memory. Okay, so let's look at this thing. So we didn't change the PC that has memory. We didn't do anything in the memory. We didn't do anything with the reg file. These are we didn't do anything to the control and status register. We didn't change any of those. We didn't add anything. Only hardware, and we didn't change the state machine. Particularly, didn't add any states to it. That's all the memory. We did make changes here, but that's just a decoder. We don't have to worry about it. So once again, if you see this problem on exam, don't say no memory changes. I want you to call out exactly what could have changed. So none of this changed. None of the memory elements changed. I did call them out directly. What else? Why this would be a very useful modification. That means particularly the RISC-V hardware as it's set up right now, it's really a pain in the butt to do jumping, branching based on bit values. Essentially, you can do it, but you just have to add extra instructions. This would make it much easier. It would get rid of the idea of a mask, and it would be quite useful. So the last question here is when would you consider putting this in your computer or not? Essentially, if you had to do a lot of control, or essentially jumping around based on a single bit. So if you weren't doing that type of jumping based on a single bit in a register, you probably, if you just did it occasionally, this instruction may not help much. I mean, it helps when you use it, but you may not use it that much. But certainly if you're doing a lot of jumping around, it's going to make your program more space efficient, and certainly when you get rid of those instructions, it's going to run faster as well. So it's going to increase both space efficiency and time efficiency. I guess that's the official way to say what this problem is doing. Okay, and I think that's all I can think of.